Alright, welcome to our physics video. We're going to be analyzing James Bond the Golden Gun using projectile motion, the three kinematic equations. Of our first one, change in position equals position initial plus velocity initial times time plus 1/2 acceleration times time squared. Our next equation is velocity equals velocity initial plus acceleration times time. And then our bottom one is velocity squared equals velocity initial squared plus 2 times acceleration. And then position final minus position initial. And in this video, we'll be analyzing a car jump scene from this video to see if it's physically possible, to see if it follows these laws, or to see if it's something that's just kind of Hollywood junk. So throughout this video, we'll be using these and applying assumptions to see if the scene could have happened. Alright, so our first assumption we'll analyze comes from the car, the information that we have from the internet on the 1974 AMC Matador. That's the car that was used in the movie by James Bond. And from the internet we saw that the car has a length of 5.3 meters. This is really important to us because on the clip we're able to gauge the length of the car kind of with our finger, gauge how long the jump was with this relative distance. Then we also know from the internet that this car accelerates from 0 to 60 miles per hour in 8.9 seconds. So we converted that to kilometers per hour, and then from here we can find the velocity of this car, the change in velocity when we get this to meters a second. And that from there we can gauge the acceleration of this car because we know the acceleration is change in velocity over change in time. So setting up the dimensional analysis to get this into meters a second, we know that there's 100,000 meters in 100 kilometers. And then we need, this is over an hour, we need to get this to meters a second. So in 1 hour, there's 60 minutes. Then in 1 minute, there's 60 seconds. So these will cancel out. And then our velocity meters a second will just be 100,000 divided by 60 times 60. And that will be 27.78 meters a second. And then from there, we can find the acceleration of the car, which is just change in velocity over change in time. So since it started from 0, this right here is our change in velocity. So we'll just put that over 8.9 seconds. And that will equal our acceleration. And doing that calculation real quick. That gives us 3.12 meters a second squared for the acceleration of this car. So using all that data we're able to, from the car, we're able to find out quite a bit about what's going on in this scene. So based off our recent assumption, we're able to find that the car was traveling 50 meters a second. When it hit the ramp, we used that from the acceleration of the AMC Matador. And then from here, we're able to make a general assumption that the ramp was 35 degrees. Just based off of the video, it looked around there. And then from here, using trigonometry rules, we were able to find the x and y components of the velocity of the car when it left. So the velocity in y was sine of theta times the hypotenuse, which is the 15 meters a second. And doing that calculation, we're able to find that the Y velocity of the car when it left was 8.6 meters a second. And then doing the same thing for the X, but using the cosine this time, we were able to calculate that the velocity in the X direction was 12.82 meters a second when the car left. And then from these velocity values, it will be crucial using our kinematic equations to make an assumption about how far the car flew and if it makes sense physically based off the video. So timing the jump in the movie, we saw the jump was 3.4 seconds, but we're assuming that this jump was slowed down by a factor of 2. It was in slow motion. So we can just divide this 3.4 seconds by 2 to give us our actual time, which would be 1.7 seconds. And then burning this into a kinematic equation, there's no acceleration in the X direction because there's no gravity. There's only acceleration in the Y. And we're also going to call our initial position 0. So we can just get rid of these terms. And we can times our velocity initial in the X, which was 12.82 seconds, times that by the time. And that'll give us the overall distance of the jump. And putting that into the calculator, we get that the jump was 21.794 meters. So based off our calculations from the previous calculation using the kinematic equation, we got that the total change in X direction would have been 21.794 meters horizontally. Then we got a height of 3.77 meters using another kinematic equation for the Y. Our target distance was 26.58 meters. That's what we calculated it had to be to make the jump. But we can't discredit this scene because there's enough discrepancies in our assumptions that this easily could have been this far had we changed the angle a little bit. We might have been off timing a little bit. That would have made our car acceleration a lot greater had we, if the time was actually greater the car spent accelerating. Also, we could have been off coming up with this distance right here, because we basically just did it by hand using the car lengths by finger as we went through the footage. So this scene isn't terribly inaccurate physically. It could happen. As we did the calculations, it's pretty close, but like I said, the assumptions that we took, they could have been slightly inaccurate, which could have taken this from this distance. But overall, I don't think that we can discredit this scene. So throughout making this video, me and Porter and Sade were reminded of some important principles in projectile motion. One of them is mass doesn't matter. When we're dealing with projectiles and we're dealing with the kinematic equations, there's no m's in the equations. So it doesn't matter if it's a 2,000-pound car that's taking off or like a baseball that weighs less than a pound. It doesn't matter. They'll still have the same calculations. And also we reminded that X and Y directions don't correlate. When we do the trigonometry, when we draw out the X velocity and the Y velocity, they don't correlate at all. They're separate calculations that we have to organize so we don't get things mixed up. And also we were just reminded that we can make good assumptions and yield pretty accurate results. Going through this video, we were able to take the assumptions from the car. We were able to time, the time that it took the car to accelerate when it reached the ramp, make a pretty good assumption on the ramp's angle, and we're able to make calculations that were pretty accurate, that were pretty in the ballpark of everything. So overall, we learned a lot making this video, and we hope you all enjoyed it.